This is Intro to the Derivative, Part 4. The first thing is just a small application. We have just found the derivative 3 different ways. Estimating it on the graph, estimating it numerically by plugging in, or by choosing 2 points very close together, one of which is the point of tangency and another point close to that, and then also using the limit of the slope to find exactly what the derivative is. So still looking at our bird problem and still looking at the derivative when x equals 2, we have this point as the point 220. So I'm going to label that again. What is the equation of the tangent line? Well, if we know the slope of the tangent line and we know the tangent line goes through the point 220, we have all the information we need to write the equation of the line. So slope equals 12, point of tangency is 220, and use y equals mx plus b and write the equation of the line. So we're going to put 20 in for y, 12 in for our slope, 2 in for x, and find b. So we have 20 minus 24 is equal to b, so negative 4 is equal to b, so that's my y-intercept. So my equation is y is equal to 12x. I've got a hesitation on my stylus here. 12x minus 4. So there's my equation of the tangent line. And if I were to graph that, it has a y-intercept of negative 4. And then the slope is 12, which means I would go up 12 and over 1. So up 12 from negative 4 would be up to 8. So basically at the point 8, 1, I would have another point. And if I drew the line through this, there's my tangent line. Kind of adjust that a little bit. There we go. Lovely, lovely tangent line. So there's the line y equals 12x minus 4. So it's very easy to find the equation of the tangent line once you know the derivative, which gives you the slope, and you know the point of tangency. Now we're going to move ahead to something a little more theoretical. I am not sure what that is doing there. It's kind of a stray, interesting. It's a stray graph here. Oh no, I'm sorry, that's supposed to be there. Never mind. What we need now is, wouldn't it be nice if there was a function that would tell me what the slope is at every point on this graph? Right now I know the slope at when x is 2 is 12, but what about the slope when x was 2.5, or when the slope is 4, or when x is 4, or the slope when x is 6? They're all going to change. This is a variable slope. It turns out that I can find the derivative function, the function that tells me the slope at any value of x. And we call this derivative function, we use the notation f prime of x. So f prime of x, and this is how we say it, f prime of x is called the derivative function. Now, notice that the derivative function is defined as the limit as x goes to c of the slope of the line between c f of c, so that would be like our 220, and x f of x, which is what we did in the previous examples. We moved that point x f of x closer and closer to 220, and we figured out the slope. But there's another way to describe that process of moving 2 points closer and closer together to find the slope of the tangent line. And that is the second definition here. Let's imagine that and this allows us actually to find the equation of the derivative function, because we don't have any specific values in for x. Here we had one specific value in for x and then an unknown point that was kind of sliding closer. Here we have just an unspecified value, and we're just going to call this point x f of x, and that's going to be our point of tangency. So I'm just going to pick a value for x, any random place, and here would be my then f of x would be my y value, and that's the point of tangency. I'm trying to find the tangent line to that point, which would be the slope at that point on the line. Now I'm going to pick a value of my independent variable on the x-axis, something close to x. And I'm going to call that point that's close to x, x plus h. So I'm going to pick another little point, and I'm going to call this x plus h. And so up here, if I go straight up and find my corresponding y value, this would be f of x plus h. Now this would be just like if x were 2. So this is an example. Let's say x is equal to 2, and then x plus h is equal to 2.1. So we're just saying something close to x. In this case, my h would be 0.1. And before, when I picked points closer and closer, I made it like 2.01, 2.001. That means h, that little difference between x and the next point that I'm picking, h is just going to get smaller and smaller. H should go from 0.1 to 0.01 to 0.001. So in other words, if you look at this definition, it says the limit as h goes to 0. So as h goes to 0, these 2 points are getting closer to each other. X plus h gets closer to x when h gets closer to 0. So I'm basically saying the same thing as I did when I went from f of x to 220, and by using points that were really close to 2 for x. I'm doing the same thing with this x and this x plus h. So in the numerator, we notice f of x plus h minus f of x. That's my 2 y values being subtracted. X plus h minus x, that's my 2 x values being subtracted. That's the slope formula. It's just a different way of writing the slope formula. Now I'm going to take this formula and I'm going to apply it to a situation where f of x equals x squared. So if f of x equals x squared, then f of x plus h means substitute x plus h into the function and square it. So f of x plus h is x plus h squared. So in my formula up here, I am going to substitute x squared for f of x and x plus h squared for f of x plus h. So I'm going to say f prime of x, that is the derivative function, is equal to the limit as h goes to 0 of x plus h squared minus x squared. So I've substituted for f of x plus h and f of x over x plus h minus x. Now, if I substitute h equals 0 into this function, the numerator becomes x squared minus x squared, and the denominator becomes x minus x. So I end up with 0 over 0. Once again, the removable type of discontinuity. This means I'm going to be able to simplify and cancel out a common factor and be able to take the limit. So let's expand this numerator. So this is the limit as h goes to 0, and in the numerator, if I take x plus h and square it, I get x squared plus 2hx plus h squared, and then minus x squared. And the denominator, x plus h minus x. Now notice that I have an x squared minus an x squared in the numerator, so that just becomes 0, so I can cancel those out. And I have an x minus an x in the denominator, so I lose any of the terms. Notice all the terms that do not have an h in them cancel out. So if I were to substitute 0 in for h again, I would have 0 plus 0 divided by 0. I would still get 0 over 0. So I need to look for a common factor. And my common factor here is h. I can factor an h out of all of the terms in the numerator, which would leave me with 2x plus h if I factor an h out of both those terms. And in the denominator, I have h. Now I'm able to remove the troublesome discontinuity because the h over h is what's giving me the 0 over 0. This becomes now the limit as h goes to 0 of 2x plus h. So now I'm going to substitute h 0 in for h, and that's going to give me 2x plus 0, or 2x. So what happens is I can say that f prime of x is equal to 2x. This is the function that tells me the derivative or the slope of the tangent line for every value of x on the x squared function. And this little graph over here is from an applet that we're going to look at online, because this is going to illustrate what we're doing with these functions. So I'm going to open that one up. And we're going to look, this is the x cubed function. I'm going to go back and make it x squared. Okay, so notice here that this is the function y equals x squared, and this is the function y equals 2x, or f prime of x equals 2x. They don't tell you the function, they just said y equals f of x. But this is x squared, and this is 2x. Now I want you to notice the tangent line here, this red tangent line, and what happens as I move the value of x. Okay, so you're seeing I'm changing the input value. Notice that when x is less than 0, the slope of the tangent line is negative, and it becomes very steep. The farther away I go, the steeper the slope. Was farther away from the origin I go. As I move closer to the origin, it becomes less steep, and now I have a slope of 0, and then I have a positive slope with positive values of x. Now I want you to notice what's happening on the right-hand side of the graph. Notice when slope is 0, the y value, and let me actually type in exactly 0. When slope is 0, you can't even see the tangent line because it's on the x-axis now. Notice that f prime of 0 is 0. So it's telling me that when x is 0, the slope is 0. So this just tells me the point 0, 0. This tells me the slope is 0 when x is 0. Now if I move x to positive values, okay, this is telling me the point on the graph is 0.32, 0.1024. This is telling me at 0.32 the slope of this graph, the slope of the tangent line is 0.64. So now we have a slope of about 1. Okay, so now my slope's getting steeper, steeper, steeper. So the y value of my derivative graph is telling me the slope of my original graph. Notice here my y values are negative now, and my slope is negative. Left-hand graph, slope is negative. Right-hand graph, y is negative. Now, if I go to x cubed, you'll see something a little bit different. So here's the graph y equals x cubed. You can see the familiar shape of a cubic graph. Notice its derivative function is a parabola. We went from a parabola to a line going down 1 degree. Now we're going from an x cubed to an x squared type of a graph. Now notice once again what happens to the slope. Right now the slope is 0, and on my derivative graph I'm at 0 here. Now if I use positive values for x, notice I have a positive slope, and I'm seeing positive values for y over on my derivative function. Now what happens when I go to negative values of y? Look at that. The slope of the cubic graph is still positive. So I have positive slope, 0 slope, positive slope again. Notice what my parabola, all my y values are positive. Except for 0, they're all positive. So I don't ever have negative slope, and the derivative function tells me I don't ever have negative slope. So we're going to go back and just put this on the graph here, and then we're going to derive the other function. So this is the graph y, or f of x. I'm going to use my function notation. F of x equals x squared, and this is the graph f prime of x equals 2x. Notice that when we have positive values for y on the left-hand graph, that's telling me I have positive slope. When I have positive, this corresponds to positive y values on the derivative graph. At the origin, my slope is equal to 0. And here at the origin, y equals 0. Then when I'm looking at the left-hand side of the graph, notice on my parabola, this is negative slope over here. And notice these are y values that are negative. So let me write down negative y. So these are negative y values. Now if we look at the cubic graph, this is f of x is equal to x cubed. and I'm going to wait for f. We haven't actually found this one, but f prime of x equals, we'll fill that in a minute. But I want you to notice for positive values of x, we have positive slope. And for negative values of x, we still have positive slope. Actually, I wanted to make one of those one color and one another. So I'm going to make this one red. Positive slope to continue my trend. This is positive slope as well. And then at the origin, we do have zero slope, where it goes completely horizontal there. The slope is horizontal. So let me write that down, zero slope. Then if we look at the derivative graph, notice that we have positive y. We have y equals 0. And then we have positive y again. So notice that we always have positive y, we always have positive slope. Let's derive the derivative function now for x cubed. We're going to do this the same way we did for x squared. We're going to say f of x plus h is equal to x plus h cubed. Kind of sloppy, I'll write that again, x plus h cubed. Now, when we do f prime of x, that's the limit as h goes to 0 of f of x plus h, which would be x plus h cubed, minus f of x, which is x cubed, all over x plus h minus x. If you substitute h equals 0 into this function, I end up with x cubed minus x cubed over x minus x, and I get 0 over 0. That means I have a removable discontinuity. If I multiply this out and simplify it, I will be able to remove the discontinuity and find the limit. So this is going to be equal to the limit as h goes to 0, and I need to multiply out x plus h cubed. And I'm going to do this by remembering Pascal's triangle. Pascal's triangle, I'm going to put this way over in the corner here. In Pascal's triangle, we had 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. When I raise something to the third power, the coefficients are going to be 1, 3, 3, 1. In other words, I'm going to have an x cubed plus 3x squared h plus 3x h squared plus h cubed. And then minus x cubed at the end. So the first four terms are expanding the x plus h cubed. Then in the denominator, x plus h minus x. Notice again, just like x squared, I can cancel out the x cubed because I have a positive one and a negative one, and I can cancel out the x's because I have a positive one and a negative one, and everything has h in it, which means if I plug in 0 for h, everything is still 0 over 0. But it also means I can factor out an h in the numerator. So the limit as h goes to 0, factor out the h in the numerator, and I'm going to have 3x squared plus 3xh plus h squared all over h. When I cancel out the h's, because h divided by h is 1, so I have eliminated my discontinuity. When I plug 0 into this, I will get 3 times, let me get back in the right color, 3 times 0, no, 3 times x squared. I'm not making x 0, I'm making h 0. 3x squared plus 3x times 0 plus 0 squared, I just end up with 3x squared. So f prime of x is equal to 3x squared when f of x is x cubed. So I can add that to my little drawing over to the left of my graph. This is 3x squared. You can see then that the derivative of a cubic function is a quadratic function. The derivative of a quadratic function is a linear function. And let me just write down what exactly does a derivative function tell me. So in between here you can fit this in hopefully. The derivative function f prime of x tells me the slope of f of x for any value of x. So I want to know what is the slope when x is equal to 3. If x is equal to 3, actually let me pick a different example because that gives me the same number. Let's say when x is equal to 1, what is the slope? The slope is 3 times 1 squared, which is 3. So at x equals 1, the slope of the tangent line is 3. If x equals -1, the slope of the tangent line is also 3. If x equals 2, the point on the graph is 2, 8, but the slope of the tangent line is 12, 3 times 2 squared. So this helps us to find the tangent line or the slope of the tangent line for any value of x. Then our next video, then we're going to look at how we're going to look at the power rule, which tells me how to quickly find these derivative functions without having to go through this whole limit process.